So not a very flattering picture of our galaxy, okay? But you guys already, before you came to this class, have a concept of our galaxy. Our galaxy actually is kind of a frisbee thing, the Milky Way galaxy. It's kind of a flat sort of thing. We have a black hole in the middle of it, and we are kind of halfway out to the edge of the disk. So our best way of seeing the galaxy is to...
No, I didn't. I sent this last week.
Okay. Our best way to see the galaxy is we don't have a spacecraft that can get a bird's eye view of the galaxy. It's so big. But actually, we can see into the disk of the galaxy if we look at what we call the Milky Way, that kind of wispy sort of... So this is the Milky Way. Throughout the year, the Milky Way will change. Our kind of perspective of looking into the heart of the galaxy changes. The term interstellar, if you're familiar with an interstate, it's basically a road that connects states. Interstellar means between stars. So actually we have a lot of kind of this dust between stars, kind of this miscellaneous dust in our galaxy. So one of the things, and we've already talked about this, we're going to talk about the anatomy of a galaxy. And the thing about it is, if you look, make sure my pointer works. When you're looking at the Milky Way, you are looking into the frisbee part. This is the disk. Okay, so this is the disk. Okay, and so above and below actually are the halo regions. And actually that, we talked about that way back. And it's going to come up again. Kind of the anatomy of any galaxy has a halo region outside the disk. And so when we look at miscellaneous stars, we're actually looking at halo stars. I think that's they are halo stars that are associated with our galaxy, but they're kind of miscellaneous. So the anatomy of our galaxy, now this actually is not... We've not had a spacecraft be able to take a picture like this. But if we were outside our galaxy, this is kind of what it would look like. And in the next chapter, we're going to talk about galaxies in general. And so a lot of the features of our galaxy, galaxies in general have them. So we have the disk component, right? Okay. We have a central bulge. And actually, if it looks nice and bright and energetic, that's because it is. I didn't track it down, but I noticed... on my Twitter feed, I subscribe to a lot of science stuff, and the caption was, "The universe is brighter than we thought." So, like usual, scientists are kind of rethinking the data they're getting, and the universe got more energy in it than they thought. But the nuclear bulge, very energetic, and that's where a supermassive black hole lies. And actually, at the end of this chapter, we'll talk about the black hole in the middle of our galaxy. The halo region, kind of above and below the disk. And then in the halo region are one of those two types of clusters of stars. You remember we said clusters of stars were born about the same time. We have open clusters and globular clusters. So we have these awesome globular clusters kind of in the outside the disk of our galaxy. We are located about here, kind of about halfway between the nuclear bulge and the edge of the disk. Okay, so we're about 27,000 light years from the supermassive black hole in the center of our galaxy. Everybody's blood pressure gets going, heart gets going a little bit faster when we talk about black holes. And just like the Monty Python song, "The Universe Says," okay, our galaxy, the Milky Way galaxy, is about 100,000 light years side to side, and I quote. Okay, notice that it's thickest at the bulge and it gets thinner out near the edge of the disk. And we're looking at about 1,000 light years, kind of at the edge of the disk. So that's kind of primary features, the anatomy of our Milky Way. So this is looking at perhaps our Milky Way not edge on, but more, not entirely, but more kind of face on. It's not entirely face on, but you kind of see a little bit of that. In the next chapter, we're going to talk about galaxies in general. And one type of galaxy is called a spiral galaxy. And you can kind of see the spiralness here. Okay, this is a spiral galaxy. Looking at a spiral galaxy, perhaps a good rendition of what the Milky Way would look like. Actually, we think our galaxy is more not just a spiral galaxy, but a barred spiral. And actually there's a bar, the bulge is actually more of a bar of stars, and we have major arms coming off and then kind of minor arms in between, barred spiral. So there are, one of the things that we talked about clear back in Unit 1 is that we're never sitting still. And so here when we kind of think of our star, which is just one of what, 200 or so, 200 to 400 billion stars in the Milky Way galaxy. Our star is not sitting still with regard to the galaxy. It cannot. If our star was sitting still, guess what? Actually, gravity would do its trick and it would fall into the supermassive black hole. So thank goodness we have a little bit of movement there. Actually, our star is taking one of these yellow tracks. Those yellow track right there is the disk stars. So the disk stars are kind of orderly. Okay, notice that they kind of bob up and down through the disk of our galaxy. The green one, the green paths there are kind of your halo stars. They're a little more random. Okay, so that's what that's showing. Yellow is the disk stars, and the green one are the halo stars. So we're never sitting still, right? So this yellow is kind of showing you the track that our sun, which is about, you know, I think very similar, kind of equidistant from the center of our galaxy to the edge of our galaxy. Our sun takes this track, and we actually, I think it might have been a question on your unit exam. How long does it take the sun to complete one orbit around the center of our galaxy? And it's about 230 million years. But the other thing is that our neighbors are actually kind of moving a little bit as we all kind of orbit the sun. So this would be our neighborhood. So we kind of are moving a little bit, but we're also definitely moving here. So one of the things, and I think it's on the next slide, and we kind of count on understanding what sort of mass we got, is by looking at the influence of that mass on something's orbit. So basically, depending, just related to the orbit of the sun, we know that inside the orbit of the sun, we have this mass. 1 times 10 to the 11th solar masses. So remember how scientific notation works, is you would like write 11 zeros. Okay, that's how many masses of the sun are in here. And actually that's how we kind of get to, well, not all of that is visible. Okay, some of that is dark matter, but it's mass. So what this says is we can get to the mass that is inside an orbit, such as the sun's, if we know our distance, in this case, to the center of the Milky Way and how fast we're going. And of course, G is a constant. I'm telling you, people, there are instructors or faculty or whatever, when they teach this same class, they make students do these problems. Okay, so it's basically we can get to mass based upon observing motion. Okay, so to me this says, how is gas recycled in our galaxy? It's going to look familiar. Basically, it's going to talk about star recycling. Okay, and we've already talked a little bit about the lives of stars, and as stars end their lives, they can actually give that material back for other stars to be born. So as we talked about galactic recycling, it's going to sound kind of deja vu. First off, to kind of break it down a little bit further with regard to that nebula of stuff that can become stars, there actually is kind of 2 versions of that. There's hydrogen cloud, and then there are molecular clouds. And the big difference between these two is the hydrogen clouds are hotter, okay, and these are cooler. So as I kind of write them, they are on their way to birthing stars. Okay, so we said that a lot of stars could be born in one molecular cloud, or one cloud, one nebula. This actually is the Eagle Nebula, where there's cute little stars being born. You guys told me on your last unit exam that the first stage of a star is its main sequence, when it starts fusing hydrogen in its core to form helium. okay, it has arrived. And whether it's a massive star that's going to burn through it quickly, or whether it's a low mass star that's just basically like the Energizer Bunny, going to like live forever as a main sequence star, seems like forever. It's the longest stage of the life of star. So regardless of low mass or high mass, it's going to end its life, okay, eventually. There's a couple different ways we talked about ending its life, actually, in the previous chapter. But ultimately, as it ends its life, and probably the more massive stars are neater to think of this way because they blow up, okay? Or they at least give a planetary nebula that can be fodder for new stars to be born. So that material that has, what we say, enriched with heavier elements can be where new stars are born. Okay, so then this actually is on its way to, after material is made available for new stars to be born from old stars that blew up or died. Okay, this is kind of on its way to actually continuing the cycle. So these next slides kind of are just basically talking about that circle of life. I think of Lion King, I think it's circle of life, right? So this actually looks like a planetary nebula, or actually at least material being given off into interstellar space where new stars can be born there ultimately. This is really a planetary nebula. This is a photograph. I can't picture what it is, but it sure looks familiar. There's a little retired star in there, a white dwarf in there somewhere, and this is kind of that cocoon of material. It's neat because we usually think of planetary nebula as kind of being circular, not necessarily. It kind of depends upon what else is in their neighborhood when that material lifts off that retired star. This is looking at something along the way of, I think this might be a supernova remnant. Okay, this actually, yeah, it says supernova remnant on it. Remnant that actually can go back to being fodder for new stars to be born. The other thing about the explosion of a supernova is it actually can be the thing that gets fragmentation. We talked about fragmentation started. Fragmentation is kind of like you have a gas cloud, and fragmentation is like those little nits that actually can become stars, cluster stars. Looking at another supernova remnant. This, it looks like something you see in anatomy or something you'd see from a dermatologist. It's like a pimple or something to me. But what you're looking at is this is the disk of a galaxy, could be our galaxy. Okay, and so this would be halo region above and below the disk. Okay, and if you read this caption, it's pretty good. It kind of talks about how we can have movement outside of the disk, it cools down, and then it rains back into the disk. And actually, I don't spend much time talking about it, but this whole hot supernova stuff, it needs to cool down in order for stars to be born, before gravity can kick in. So this is actually talking about the two types of nebula. I know it says molecular cloud up here, but a molecular cloud is a nebula. The molecular cloud that's kind of hot, the hydrogen cools down. And actually, this is something we talked about. Do you remember we talked about adding energy to stuff for it to break apart? And I started with adding energy to a solid, like an ice cube, if it melts. Adding energy to liquid, okay, like water, it evaporates. Okay, adding energy actually to molecular water, that thing's going to break apart into, we know it's got hydrogen and oxygen, that's what water has. Okay, so it's going to go from being a molecule to being elements, and that's kind of what this is talking about, cooling down. So Orion is rising earlier and earlier. Okay, Orion is a beautiful constellation. And this is, here's Orion. And so here's Orion's belt, and here's Orion's sword. And Orion's sword actually has a molecular cloud where stars are in the process of being born. This is the Eagle Nebula, again, where stars are being born. So remember what the title of this chapter is. This chapter is all about us. This chapter is all about our galaxy. Okay, so one of the things I'm hoping that you kind of get a handle on or sort in your own mind is, for instance, I'll kind of draw your attention to the Messier objects again. Okay, when we talk about stars, when we talk about clusters, you can kind of see from your vantage point kind of these clusters of stars, okay? Those stars, the Orion, the globular clusters, the open clusters, the nebula, those are all part of our Milky Way galaxy. We're going to switch gears actually for the last chapter in this unit and talk about other galaxies. And it wasn't until like 1923 that we understood there were other galaxies. Like, dude, oh my gosh, really? Okay. But if we look at the Messier chart again, there are some wispy sort of kind of elongated things. I don't even know from your vantage point if you can kind of see some of these are galaxies. The things you see naked eye are not generally galaxies. They're stars or clustered within the Milky Way galaxy. So, kind of summarizing what we saw, I'll just put all these up here. And it just very much, I know it says galactic recycling, but it's more of the recycling of stars within a galaxy. Okay? And it's nothing entirely new to what we were talking about. So I think I said somewhere along the line already that our solar system, we know, had to have been made out of stars that lived their lives and gave material back. Otherwise, it would just be, we'd only have access to hydrogen. Okay. The reason we have heavier elements was because it was fused or forged associated with either the star living its life or a star dying. So these are all the Milky Way. These are all looking at that wispy, okay, kind of band across the nighttime sky. But they're looking at different wavelengths. And we're going to kind of look at them one by one. I'm going to start with this one right here. This is visible light. Okay, so this is just looking at what visible light the Milky Way can send us. You probably see these right here, this right here. Sometimes it's called dark lane or dark lanes. There's not an E on it. Okay, the dark lanes in the Milky Way. But that's only in the visible region. Does it look like dark lanes there? Okay, so actually, when we look at these, this right here, as we look at all of them, this is the center of our galaxy. Center of MW standing for Milky Way. And it actually has a BH, of course, standing for black hole. And I think somebody asked Friday, it's like, well, black holes, how can black holes be that shiny? Okay, you're like, what? Okay, so here's the deal, is that energy that we're seeing is on the other side of the event horizon. It's not like it's leaving the event horizon. But I would say the black hole that's hiding, it's not really hiding, is creating the commotion that's creating that energy that is on the other side of the event horizon that we see. Okay. So this is looking at the Milky Way again in X-rays. So as you see all of these, you probably notice a pattern where this is the longest wavelength, okay, and the least energy, okay, and this is the shortest wavelength. We're going to get to gamma too. And this is the most energy. So each wavelength, actually, if you're a scientist, if you're one of those sort of people, each wavelength tells you something different. So the infrared told us energy, thermal energy. X-rays actually tell us focus on hot gas in the halo region, above and below the disk. Then going up to something even longer than infrared, radio waves. not just any radio waves, but sometimes you'll hear astronomers say it's the wavelength of 21 centimeters. You're like, get out a yardstick, okay, or a meter stick and find 21 centimeters. That is the wavelength of energy that can tell us something very significant with regard to atomic hydrogen. Okay, the next one is kind of related to that. A little bit shorter than 21 centimeters in the radio region of the electromagnetic spectrum or energies. And actually you can go from elemental hydrogen to molecular carbon monoxide. You know, the stuff we try to make sure it isn't in our house, carbon monoxide. And the significance there is it has cooled down. Okay? And the significance of cooling down is that within that molecular cloud, that's what's sending you the signal, you can begin to maybe think that stars are going to be born. So here in the disk you see where stars can be born. So kind of bridging the gap between infrared and the radio waves that gives us carbon monoxide is this other infrared, long wave infrared. It's kind of showing us where the dust region is. The last one we have is down here at the bottom, and that's gamma rays. See, gamma rays are telling us where some of those stars are blowing up. Supernova are occurring. And I'm glad we're out here, quite frankly. Okay, so remember the sun is out here with regard to the disk of our galaxy. Because actually, in that, we talk about the Earth being at the right distance from the sun and the right size and all that. But you know what? Our sun needs to be at the right location in the Milky Way galaxy. And I think that's probably unappreciated. Okay, if we were, anyway. Okay. So I have some pictures of nebula and different types of nebula I kind of want to talk you through. Now, nebula, we said, is a cloud, a dust cloud. Okay, usually you go between stars and there's nothing, it's a vacuum. But between stars and there's something, it's a nebula. This is an ionization nebula, and it simply means that electrons are being excited, okay, and then they fall back down. Kind of like our light bulbs work. Okay? The gas has gas atoms, have a nucleus, and they have electrons. Electricity is exciting those electrons, and they fall back down, they give us light. So that's why we see this sort of nebula. That's why it glows. This is another type of nebula, and the reason we see this nebula is by what we call reflection. And I know it says reflection, but it's more like scattering. Okay, so basically, does it kind of remind you of maybe fog and dust to me? Okay. If you've ever kind of tried to look at, if it's been foggy and you try to look very far away, your visibility is cut down. And the reason your visibility is cut down is if you have a light that's beaming in all directions, that light is scattering on those liquid water particles, the fog. Okay? And that's kind of what I think of this. This actually, I know it says, what kind of nebula do you see? And I should answer that because I don't know if you see like a little chess piece here, like a rook. Okay. I don't play chess, so I was making sure that I think that's right. This actually is a dark nebula. Remember a little bit ago I said if you look at the Milky Way with binoculars, you're actually going to see those dark lanes that I talked about. Okay, those dark lanes in the disk. And those are kind of similar, very similar to what they are, dark nebula. A dark nebula doesn't mean that there's nothing there. A dark nebula means that there's something there and it's not lighting up. Okay? That's what a dark nebula is. All right. So I'm going to kind of make some compare and contrast of material in the disk versus material in the halo region. Okay, you see the disk here. Okay, and as it turns out, if you are a young family, okay, this actually disk area is where you want to be. It's where it's happening. That's where stars are being formed. If you're ready to retire, okay? Or on the other side of having your children, your family, where you want to be is in the halo region, okay? So the halo region are older stars, no new stars are being born, no whippersnappers to cross your yard, okay? Here in the disk region is where you still have activity with regard to stars being born. So this is a photograph of a galaxy, another galaxy, and it's called the Whirlpool Galaxy. So remember in astronomy, as they name things, sometimes they give them names like M101 or NGC 605. But then sometimes the same objects have cool names, like the Whirlpool Galaxy. Okay. So another spiral galaxy, and we look at other galaxies to get a hint for what might be happening in our own galaxy. So this slide is kind of emphasizing those spiral arms are where you actually have a lot of stars being born. And this slide is trying to tell you, why do we kind of have like a spiral arm with a lot of stars being born? A lot of times when we look at other galaxies and within our own galaxy, our spiral arms are packed full of those beautiful blue, hot, we talked about the 7 spectral types of stars. OB, fine guy, girl, kiss me. The OBs are hot and they live their lives quickly. And those are the ones that actually are in spiral arms. Well, if you look into it, it'll talk about something called density waves, and it's because of these kind of density waves are coming that keep this movement of these fast-paced stars in these spiral arms. Okay, so again, compare and contrast. So we have, you can't see it much, you can see the dark lanes, right? We're looking at our Milky Way, looking at it from the disk view. Of course, we have the disk and we have the halo view. Okay. The thing about the disk stars, I told you that's where young stars are still birthing new stars. Okay, they're fast livers. Okay. And it does not seem like much, but I'm going to go ahead where it says heavy elements, 2%. I'm going to put that is a lot. Just the word a lot. Because if we compare that to, oh, by the way, before I go to halo. So down here, and I can't remember if Bennett actually includes this in his, but I included my slides. I don't know if he has it in his essentials of cosmic perspective. Because it's going to be backwards. We actually call these disk stars population 1. Disk stars equal population 1. What does that mean? It means they're relatively new. Disk stars equal population 1. Okay. So compare and contrast. So I told you those halo stars, globular clusters, and actually globular clusters are older stars too. When we look at how much with regard to things other than hydrogen they have, they are very lacking. They only have 0.02 to 0.2%. So I'm going to put not much. In fact, I'm going to add one more term I think helps. We actually call these metal poor. Okay, I'll put a frowny face. I don't know if they're really sad about that. Over here, I'm going to call these guys down here in the disk, I'm going to call them metal rich because I put lots next to that 2%. Our sun, I'm hoping you guys would tell me it's in the disk. Our sun is metal rich. Our sun is one of this newer generation. Okay. The reason they are metal rich, one more thing to kind of emphasize what I'm trying to say here, the reason they were metal rich is they are made from earlier stars. Earlier stars. How about this? Made from earlier star stuff. Yeah. These guys up here are kind of the original stars. Now that's kind of creepy. Original stars from what? Ooh, original stars from the Big Bang-ish. Some of these guys up here actually push the age of our universe. Okay, so it's backwards, and I kind of apologize, kind of don't. We call these older generation population 2. Seems backwards to you, it seems backwards to me, but that's what it is. I can remember, several years ago, getting ready to teach this for the first time. I'm like, are you sure that's what they mean? Population 2 are like the first generation. Okay. Again, it may not be in your textbook, but it's on my slide, so it's fair game. So here's the deal, generation. Gosh. There we go. The first generation. Several years ago, maybe 6 years ago, actually it caught my eye because in the things, the journals and stuff that I kind of look at was population 3 stars. You're like, dude. So it was like even earlier than in general. So I'm kind of throwing in a term anytime in your textbook and kind of in this unit of material. If you hear anything about spheroidal, I can't pronounce it. I think of that word, spheroidal, is kind of think of like a football sort of thing. And spheroidal actually still means halo. So when we talk about spheroidal population, we're talking about the stars in the population in the halo region. Oops. Oh, wrong keyboard. Okay, so again, these guys here, and we're looking at it edge on. So we're looking at the disk. We're not looking at face on. If you look at face on, you'd see spirals. You're looking at it edge on. Actually, this is in the disk region is where new stars are getting formed. So we're going to talk more in actually the next unit of material. I can't remember if we talked about it when we talk about just galaxies in general, but it's like, how do you get a Milky Way galaxy? Well, it's kind of like how do you get a star, except on a large scale. So you need to have a big, humongous gas cloud. Why humongous? Because you're going to have you're going to have like 200 billion stars being born there. Like, really? Really? And that gas cloud that's going to form a galaxy of stars needs to have a certain amount of rotation. So there's your spin, okay, and the rest is kind of history. Okay, and the center actually is going to be where most galaxies we think has a supermassive black hole in the center. Okay, so as a galaxy ages, okay, then we have stars being born. They live their lives according to kind of the rules we talked about in the last unit of material. Okay, the massive ones will live fast and furious, and the lower mass ones will just kind of keep on ticking. So your author warns that kind of how I've described the evolution or kind of the lifespan of a galaxy of stars is very oversimplified. This slide just kind of talks a little bit about in the halo region where we had those clusters. We had globular clusters of stars. Those are the low mass stars that have been there ever since. Okay, this kind of talks about how they clump together. So I'm glad to kind of get to this last topic. So we're kind of winding things down, and we'll be talking a little bit more about black holes that are in the center of galaxies when we talk about galaxies in general. But to focus on the center of our galaxy that has a supermassive black hole, I have a series of slides that gets closer and closer. And these series of images actually have a variety of wavelengths. So this is looking infrared, and you can kind of see ballpark 200 light years is that much. This is honing in to 50 light years now and looking at radio wavelength. Scary, not a good place to visit. So this is honing in even closer. Okay. And this is actually, again, looking at a different type of radio wavelengths. And this is back to infrared. So it's funny how you can look at different wavelengths and see different things. I guess that makes sense. That's what we've been talking about earlier in the class. But where those arrows are, this is 1 light year drawn to scale. So a part of a light year actually, then that is where our black hole is. So, of course, the age-old question, how do you know there's a black hole in the center of our galaxy? And by the way, and I'll try to maybe point this out later, if you're familiar with the nighttime sky, and hopefully you're coming a little familiar with it, the Milky Way, right? The Milky Way? One of the constellations that's in the Milky Way is Sagittarius, the Archer. And if you're like me, I can never find Sagittarius, but I can find the teapot. A long time ago, we had to talk about the teapot. If you can find the teapot, which is a subset of Sagittarius, the teapot has a handle and a spout, and where that spout is, actually, that right there is where the center of our galaxy. Okay, and so it's not so surprising when we call the center of our galaxy the black hole. That object has been called Sagittarius A. Sagittarius actually A star. Why? Because it's in the constellation Sagittarius, specifically the teapot. Okay. So anytime somebody talks about Sagittarius A star, they're talking about the black hole in the center of our galaxy. So basically, it's kind of back to what we talked about when we said we know how much mass is inside the orbit of the sun because we know the radius and we know the velocity, so we can knock out the mass. Similarly, what they've done is, and you can see the mass of Sagittarius A star, the mass of Sagittarius A star is 4 million times the mass of our sun. You're like, dude, how did you know that? Well, they knew that. Oh, I'm going to go back one more. They knew that by watching stars orbit that object. Okay, they know the mass by watching stars orbit that object. And they know its area by they know its area because they get images of it. Okay, so basically, they know that mass, that 4 million solar masses, is crammed into this small area. So kind of go back to white dwarf, neutron star, black hole. Neutron degeneracy cannot support the matter being crammed into that small space. So it's a density thing. This is a really short video. It's a classic. I think it's 15 years they tracked. What you're seeing, those little dots, are actually are stars orbiting Sagittarius A star. I don't think there's any sound. Blink and you miss it. It's 11 seconds, so we'll play it one more time. Okay, so that number at the top there is years. (1995). That's the motion of stars. 2002. They tracked all that. And you can get at the mass of Sagittarius A star. Then the only missing link you need is its space or its volume, and you can get to its density and know that it is a supermassive black hole in the center of our galaxy, Sagittarius A star. So this chapter homework will be due when we meet again on Wednesday. And so, yeah, let me know if you have any questions about that Rosetta thing, but it's before class. You could have a Rosetta party.
Did you say that Rosetta thing was a lab?
Yeah,
Like
worth
we do
lab
at some of
credit.
our labs?
Uh-huh. Yep. And extra labs, if you have more than 4, you can count them for assignments too.
And I can email you my homework assignment, can't I?
Yes, you can. Especially if you tell me ahead of time, I'll be looking for it.
Okay, I'm emailing it to you. I was
Okay.
going to do it after I signed up for my spring classes, and then my daughter ended up coming home sick from school, so I was busy doing that all morning.
Lucky you.
That was going to be one of my notes too, that I was going to be emailing that to you.
Okay.
If that's okay.
Thanks for letting me know.
Can I email you my lab write-up too?
Definitely, especially if you just need to maybe follow up and make sure that I get it. You know what I mean?
Right,
Sometimes
right.
I like,
Just to
that
double
sounds
check.
good. I'm glad you made it out to observatory.
Yeah, we really liked it. We had a good time.
Good.
Can I get you to sign?
Yeah.
Here
Did you have a quick
from
question? Hannah?
October.
Yeah, I don't know if that, I don't know what that girl asked. Since I was sick.
Are you feeling better?
Yeah, kind of, but, I just didn't want to miss any more school.
Yep, thank you.
I just didn't want to miss any more school because I didn't want to get too far behind. Can I email the chapter 14 assignment to you? Like type it up and email
Yeah,
to you?
that's what she asked too.
Okay,
Yeah.
I didn't know if that's what she asked. I
Yeah.
heard her say something about emailing it to you, and I was like, I wonder if she asked the same thing
Yeah,
I did.
and
But just to be sure.
I don't prefer that because sometimes I'll like lose it and stuff.
Yeah,
but
well,
especially
the only reason I asked is because since I was sick on Friday, I missed a test, and that's what I'm going to do right now.
Oh, yes.
And then I have a class at 1, and then I live 40 minutes away, so then I was
Oh,
going to
yeah.
go there. So that's
Just
why I asked
email
it.
it,
Because
yeah.
if I didn't have to take the test now, I would have done it within this break, this hour break that I had. But since I'm taking tests, I just
you're
wanted
trying to make it all fit. In fact,
Yeah.
this would apply to any of you 3 guys or whatever. You can, as long as it's by midnight tonight, that would be great.
Oh, okay.
Yeah, because that's what I was hoping to.
Yeah, I'm doing
work.
all my catch-up work today and tomorrow, so I'm trying to figure out what I can do, figure out the order I'm supposed to do it in for the most part. So
That sounds good, Hannah.
Okay, thank you.
You're welcome. Astronomy. Right. Do I initial it somewhere?
Yeah, just at the end.
Oh, right here it is.
Yeah.
Signature. They're really picky sometimes. All right.
Thank you.
You're welcome.
And did I was just wondering because I did miss last week when we went over the test. Or did you put the grades up yet?
Yes, I think so.
Yeah. Okay. Okay. I just wasn't sure. I checked my email, but I didn't have time to check my
Yeah.
the grade book yet. So
Let
I
me
just
know if
was
it's not up there. but-
Curious.
Yeah, I think you did very well, so.
Okay. I
And
think
your-
I did too.
Your exam's in my office, so you'll have to like stop by or something.
Okay.
But it's definitely there for you.
Hey, cool. Thank you.
And did you get your quiz done? Did you finish your quiz?
No, because I haven't gone over chapter 14 yet, so
Okay.
I didn't
Well, you wrote
have
something
anything.
down, right?
Yeah, about the Rosetta Stone to watch, like the notes and
Oh.
stuff on when to watch the time. And
Well, those
NASA.
quizzes you could have asked me and I would have told you. So I'll put you down for credit anyway. They're not. Yeah.
I'm just like, well, I know
No,
there
they're-
are 2 different types, but I couldn't remember them.
They're not. And also, it's like the one that where star goes up. There's like massive stars. Like if it's more than 8 times the mass of our sun, it's its life, and that's where you get a neutron star black hole.
And then that's from okay. So that's the 2 different.
That's one.
Okay.
That's called the type 2.
Okay, we went over that one last year.
And then the only little this unit that's new is that we actually have a white board that contains a golden star. And the golden star jumps on the white board. If it blows up, that's a 1A. So they call that a supernova.
And the other one you said was called type 2 supernova?
Yep.
1A. Okay, that makes sense. Okay, now I understand the difference here. All right, thank you.
I woke up and found out that I flat tire. My brother changed it for me. I got a patch that could work. My car is still there, but I'm going to take it over here in class. It's been a great day. I've been using the trip for hours.
hate Halloween was taken down. Was my